All right. So thank you and welcome. This presentation has been in the planning for a couple of months now, which you probably couldn't tell from the quality of the content, but the idea of this presentation is based on the imminent release of the Project Azumeral Viewer. The Project Azumeral Viewer is writers' reworking of the viewer HTTP code to get rid of the old, the crufty old LL curl machinery. Apologies to anyone still around who had anything to do with that. And replacing it with Monty's super cool LL core HTTP machinery. In the process of doing that, Ryder has also, since he had to touch a startling variety of different places in the code, has also introduced the coroutine pattern into many of those places. And so what we want to do is to introduce to you what that code looks like, what it does, and hopefully give you a level of comfort not only with seeing it and working beside it, but hopefully being able to write that pattern yourselves, because this is the official pattern going forward. And so if you have questions about how best to use it, please direct them to either Ryder or myself. So we're going to switch over to a bit of PowerPoint. Okay. So we, of course, are trying to explain a fair amount of technical detail in a short amount of time, but we did schedule long enough to allow for questions. And if you have questions, we would much rather that you ask them than go away distressed, confused, dismayed, disbelieving. So for those of you who haven't worked with the viewer for a while, or who maybe have not worked with the viewer at all, the viewer is like a classic event-driven program, mostly in a single thread. There are notable exceptions, but so far the viewer's business logic is in a single thread. There are specific other threads for specific other purposes, but for the most part, classic viewer logic is in one thread. Like a classic event-driven program, the viewer is responsible, that single thread is responsible for handling mouse cursor updates, for dealing with the user's keystrokes, and in general for presenting to the user the appearance of a snappy responsive application. So we can't allow the viewer to wait. We can't allow that single thread to wait for much of anything. Otherwise, the moment it does, the user's experience starts degrading. So there's a whole lot of async I/O going on in the viewer. The business logic initiates an I/O operation, arranging for control to reach some kind of callback, and then returns the main loop so that it can carry on with the processing of the other essential stuff. There are a dismaying number of different patterns that the viewer uses to handle async I/O. You might almost think that over the course of its 12-year lifespan, each new developer who was faced with this problem treated it as a whole brand new problem, as if none of us had ever encountered it before. So I'll illustrate some of those patterns, the common ones. The responder pattern is kind of lifted straight from Java, where you have a base class with virtual methods that get called on success or error. So in any particular usage, you derive a subclass, you override those virtual methods, you instantiate your subclass, and pass a pointer into the async IO operation. You initiate the IO and then go away, return to the main loop in a sense. So the setting up the call and the processing the results are broken into a separate method of a separate class. And so poster child is in LViewer region. We have a responder. And please shout if this code is too tiny to see. I don't think I can do much to expand it on the presentation screen, but these slides will be available after, as will writers. We derive a base capabilities complete subclass from LLHTTP client responder. You can see that there's an error virtual method override, which isn't interesting here, and a result virtual method override. And whatever it does in there, it processes the result of the call that was set up by a completely different bit of code. This is the different bit of code. Set seed capability. Look at the bottom two lines. Base capability is complete, has a static function, static method build that instantiates the subclass, and then we take that pointer and pass it into LLHTTP client post. Another of the patterns that you find is the big switch statement. This is kind of a seductive pattern in that, as the name implies, you have a function body laid out as a cascaded sequence of states where each state is mediated either by a switch statement, literally, or as in the case I'm going to show you, with cascading ifs. And so the seductive thing about it is that it kind of looks as if control is going to flow smoothly from one state to another. That's illusory, unfortunately, because every time you make a state transition, you are actually leaving the body of the function and going back to the main loop. On the next entry, the control variable is used to send control back to the current state. The unfortunate effect of that is that you can't count on local variables. None of the local variables in that function are going to remain valid between calls. And so one problem is that all of the interesting state has to be kept in global variables, which we do. And but the other problem is that the fact that control must return from this function every tick means that there is no encapsulating any helper functions. All of the relevant logic must be in line in the function body. And so as you add sophistication to the state machine, the function body literally unbounded growth. So we'll look at llstartup.cpp. Its idle startup function is 1900 lines. When I first was poking at it a couple of years ago, it was only 1700 lines. So we've acquired quite a few additional lines of logic in line in this method in the last couple of years. And as you can see, it just tests llstartup get startup state, which is an access method for a static, and compares it to different state values. But you can see that each of those cases, having done what it's going to do, returns from the method. Then there's the state machine pattern, and this is where you are starting from a base class which represents one of the states of the state machine, and then you derive distinct subclasses to represent the different states. And there is a canonical pointer in the parent state machine class holding a polymorphic reference to the current state in which the state machine finds itself. And so as you transition from one state to another, you call the exit method of the current state you call the enter method of the new upcoming state. So we'll look at llogin instance.cpp. The mandatory update machine, of course, has a state-based class. We see here deriving a couple of subclasses from it. One is checking for update, one is starting update or service, and you can see the enter and exit method declarations along with helpers. So looking at checking for update enter, we see that it is arranging to receive notification on an LL event pump. And I'll talk a little bit more about LL event pumps in a minute. But basically, it's a way of getting a callback. And we see that it's setting up to receive a callback, again, in a completely different method on the same class. So all of these are kind of sort of okay when you're dealing with one level of abstraction. If you have one responder, okay, you can follow that. If you have a couple of states in the state machine, okay, fine. When you are transitioning in a straightforward fashion through a chain of responders, sigh, it's tedious, but you can follow it. The real problem is when you're trying to do anything more sophisticated. If you look at idle startup, for instance, the control does not smoothly flow from one state to another. Actually, you have some kind of fancy jumping from state to state during the course of the execution of the program. This is kind of like, go-tos being considered harmful. It gets even worse when you are dealing with these with a class-based state machine. And I was working in Manny's group some years ago, and Manny had extracted a substantial chunk of the idle startup and taken it from the big switch statement pattern to a state machine-based pattern in a whole other source file. So reducing the size of that giant method, yay, that was great. But for me to figure out what the logic flow in his state machine was, took a significant amount of reverse engineering. And what I ended up with was rewriting it as a coroutine. And the cool thing about coroutines, a couple of cool things. It reads like sequential logic. You can use the ordinary C++ keywords to mediate control flow. And so if you want alternatives, you write an if. If you want looping, you use for, while, or do. You can use local variables. They just work. So if you look at the login underscore method in llogin.cpp, if you look at this admittedly somewhat thick for loop, this post and suspend function actually causes control to pass back to the main loop, leaving this coroutine waiting exactly here for the next event that it desires. It wakes up here in the same place when it gets that event and continues with the processing of the for loop. Similarly, suspend until event on passes control back to the main loop, waiting for something interesting to happen. But the loop, the thing that was so hard to figure out when I was trying to, reverse engineer Manny's class-based state machine, the loop is obvious. You don't have to have taken more than a couple of courses in C++ in college to be able to understand that there's a loop going on here. How do we do that? The key thing about a coroutine is that each coroutine has its own call stack. And so, because local variables are stack-based, stack variables persist. So you have the ability to switch the processor's stack pointer from its original OS allocated call stack into this other call stack, do some work, and transition back. So looking at that, we have the main loop chugging along. And meanwhile, over on the right hand, we have a suspended coroutine. The main loop gets to a point where it decides to call a particular completion callback. The coroutine has previously arranged that that callback is going to resume the coroutine. So it wakes up and does something on its own stack, evaluates logic in the way C++ always evaluates logic, and then it makes a suspend call again. This passes control back to the main loop by returning from the completion callback. And then the main loop goes on to do whatever else it was intending to do. You can think of coroutine machinery as permitting a kind of inversion of control. This context switching between the two stacks looks like a function call to each side. The main loop calls a callback, which causes the coroutine to return from suspension. When the coroutine wants to suspend, it calls a function, which causes the main loop to return from its own function. And this is in stark contrast to the problem of, let's say, the big switch statement, where control has to return out of the function body every single time. So having a stack, being able to use normal C++ idioms extends to being able to refactor using encapsulation. You can use helper functions. You can suspend from the middle of the body of a helper function. That works. A coroutine does not run on a different CPU. And so coroutines do not provide better distribution of work across multiple processors. The good thing about that is that they are not racing for access to our shared data. This is crucial, especially for our viewer. I think that anybody who has worked with the viewer for any length of time will agree with the assertion that most, I won't say all, but most of our many, many, many source files each have a bit of static data of their own. I will further assert that if we introduced multiple threads to organize our code, the effort to discover and defend every single bit of static data from racing threads would be prohibitive. It would be cheaper to rewrite the viewer from scratch to be thread safe from the ground up than to retroactively defend each bit of static data on which the viewer relies. Coroutines do not require the locking, the critical sections, the mutexes. Coroutines trade the processor between them cooperatively. So you know that only one coroutine is going to be touching your static data at a time. It's an organization tactic. It doesn't introduce new parallelism. It's just a better way to write code that would have been written as a responder or as a big switch statement. So maintenance, it not only reads better, but it's easier to work with. You have some existing logic. It makes a couple of different async requests already, and you have to insert a new async request in between them. Well, if it's a chain of responders, you have to, of course, create a new responder subclass. You have to split the logic in the responder subclass method that handles the first completion, initiate the operation, migrate the post-processing code into the new responder, and oh yes, any local data that you care about has to be passed explicitly from the first responder into the new responder. If you are dealing with a big switch statement, you have to, of course, create a new state value and a new clause to handle it. You have to move any local data that it cares about into global variables, and you have to verify that you haven't screwed up the existing state transitions. In the state machine, actually, this is rather like the responder problem. you have some, response method, you have to initiate the request and split the logic before the request from the logic after the request and move the post logic to the new state class. With a coroutine, you just insert the call. It looks like a blocking call. It acts like a blocking call from the point of view of inspecting the coroutine. And you don't have to move the local data because it just keeps working. So that's something about coroutines and why they're interesting. Here's some about the machinery that we have introduced into the viewer to support them. There's an LL-Coros class. It's a LL singleton. Those of you familiar with LL singleton know that LL-Coros : instance gets you the canonical instance of the singleton. Its launch method starts a coroutine. You pass to it any nullary callable. A callable, a free function with no parameters. It could be a static class method with no parameters. It could be an object with a parameterless operator pren. It could be a boost bind expression. And, pro tip, what boost bind returns is literally an object with a parameterless pren method. What is even cooler is that as soon as we allow ourselves to use C++11 features, C++ lambda will also work as a callable in this context. When you pass any one of these things to LL-Coros launch, that code immediately starts running. And one of two things will happen. Either it will reach a suspend point, at which point it will pass control back to it will return from the launch call. Or perhaps the coroutine will decide that it has no work to do and will return without suspending. Same thing. Either way, control returns from launch at that point. Okay, I'm going to detour a little bit to talk about LL Event Pump. There are many programs that have a single event bus that mediates all of the significant events in the program. LL Event Pump gives us multiple event buses, and so you get to register for whichever set of events you care about without having to filter and discard events that you don't care about. LL Event Pump is an API class. I usually talk about LL Event Pump, but LL Event Stream is actually the concrete implementation. LL Event Pump is just a wrapper around Boost Signals to Signal. As you know, Signal is a container for callables. And so it has a producer-consumer API. Consumers register themselves to receive callbacks, and the producer will call the signal with some payload, at which point each of the consumers will receive that call. So in our API, an LL Event Pump has a listen method. So you listen for events on the callback. The post method on LL Event Pump receives LLSD and passes it to all current listeners. There are a number of different ways of disconnecting, but I'll call out LL temp bound listener because that is a scoped connection. When you call listen and you store the return value in an LL temp bound listener, then when the LL temp bound listener is destroyed, it implicitly disconnects that connection, which is very handy. As I was saying before, LL Event Pump instances are named singletons. So each LL Event Pump has a string name, and you find them by string name by querying the LL Event Pumps singleton, which manages them. It uses finder create logic, which decouples order dependencies from the producer and consumer. Either can ask for the event pump first, both will be connected to the same instance. So around the LL Event Pump machinery, we've built some convenience methods. There is the post and suspend call, which we've seen in the LL login example. When you have, so an LL Event Pump can be thought of as a simplex communication channel. one producer, some consumers. So if you want duplex communication, as in request response, what you do is you arrange for a pair of LL event pumps, one for each direction. And so you can post to one event pump and then wait for a response on another event pump using this post and suspend method. Why conflate the two things? Because there are circumstances in which your post might produce an immediate response. And if your logic is such that you do the post and then arrange to wait for the response, you'll miss the response. But if you're not posting, if you know that the event source is already going to be producing events and you just want to wait for the next one, you can use suspend until event on instead. And then because, again, we can't allow any logic in the viewer to delay returning to the main loop for any length of time, you can sprinkle suspend calls into your logic to ensure that control returns to the main loop. Suspend just waits there for the next tick on the main loop. So this all is based on the LL event pump machinery. It is not hard to write adapters for other kinds of callbacks, but we started using the LL event pump machinery, and so far that's been adequate for our needs. If you need to glue onto a different kind of callback on which to suspend your coroutine, let me know, or Ryder. Okay, so as we've noted, we have a ton of global variables and other shared resources. But as I was just saying, a coroutine is no more dangerous to access those shared resources than code in a responder or a big switch statement or a state machine. It's just an organizational tactic. Monty asked a fabulous question. He said, okay, bear in mind that there is a main loop mechanism that time boxes network completion callbacks. And so you have some set of callbacks that have come ready in a given iteration of the main loop. The main loop reaches that point and decides to allow a certain time frame in which it's going to process completion callbacks for that iteration. And then it calls as many of those callbacks as can fit in that time frame, and any that remain, it defers until the next iteration. But coroutines don't change that mechanism. The main loop decides to make a call. That particular completion callback resumes the coroutine that's suspended. The coroutine will execute until another suspend point or its own exit. Control returns to the completion callback and returns to the main loop, just as if it was organized as a responder or any of the other tactics we've been discussing. The main loop has exactly the same opportunity to time box the whole thing. It doesn't know that what it was doing is resuming a coroutine. Performance. So we are talking to the big bad internet, to our colos and to S3 and to various other things. I don't care how many cycles it takes to switch from one stack to another. We're talking about milliseconds of time to go over the network. What about memory overhead? The current coroutine default stack size is 256K. So if we had 1,000 of them, I'd start to worry. Exceptions, we have them, we deal with them. It's not a problem. What happens if we don't return to a coroutine? Well, if you destroy the coroutine object, actually the library will throw an exception at the suspension point that unwinds the coroutine stack and cleans up stack variables, just as such things would normally do. What happens if we don't even destroy the coroutine object? It's the same thing that would happen if we never call a responder. It just sits around. It's not a new problem. And we do have a timeout mechanism. Cluttering the code? Well, what did it look like? We had a post and suspend call. Okay, the logic in the for loop was perhaps unnecessarily ugly, but we weren't looking at the mechanism to arrange to get control on the callback. We were making a function call that suspended. And that, again, is because having a coroutine stack lets us encapsulate the messy details of interacting with the coroutine machinery. We can just say, okay, I'd like to suspend. And actually what you'll find is that Rider has taken this level of machinery and wrapped it in further levels of machinery that are just normal C++ encapsulation. And finally, I assert that using this pattern, by making it easier to reason about the control flow, by permitting us to use local data instead of putting yet more stuff into static storage, will make the viewer more robust. So I think before I give this over to Ryder, I'm going to ask if anybody is puzzled. So I'm looking at the chat stream.
Oh, there's one. Okay. What about the crash dump? Is it possible to see all the states in all coroutines? From Ruslan.
So that's an interesting question, and I don't know the answer. I don't usually work with crash dumps. I will be fascinated to try to poke at that with you. I think what you'll find is that there will be a current stack. The current coroutine will be what is identified by the processor's stack pointer. I think that it would probably take a little bit of digging around to locate the other stacks, which are in effect blocks on the heap. And could or should we introduce ways to make that more clear? Yes, we could. And if you are going to be working a lot with viewer crash dumps, then probably we should. That is possible. But I would say that we haven't got that in place yet. Okay, I'm going to hand it over to Ryder.
All right. Let's see.
And meanwhile, I'm going to address Aura's question, which is, since we can probably override the coroutine class in unit test, we can then make those other parts of the code much more easily testable with automated tests. I think what you're saying, Aura, is that we need not run the code in question as a coroutine. And that is in a test framework. And I think that's mostly true. I think the interesting question is, we will need to arrange to simulate a tick on the main loop, but we actually have cases now where we're unit testing code that normally runs in a coroutine. And I do provide simulated main loop ticks to kick it and keep it moving. Okay, Ryder.
All right. I'm just chuckling over Oz's comment. All right. So we've talked a little bit about the underlying technology behind the coroutines. And I wanted to start off with just a quick review of the LL curl responder and its work with the HTTP client, which is the most frequent of those described patterns that we've been replacing. Just for the record, here's very simple picture. A responder has a on completed. virtual completed, which calls either a virtual success or a virtual failure. There is the same thing in a less pretty, more code-centric. You'll notice that the completion, the failure, and the success, as I pointed out in the image version, are all virtual, which means that subclasses would override them. Very much the way we've done, very much the way I've done here in this sample. This is just a very simple responder. It overrides the success. Just send something to see out. You'll notice that it's passed to either a get or a post. The pattern that we were using was to allocate the responder descendant directly in the call to HTTP client. This pattern separates the success and failure functionality. In many cases, you will get a network success that should be interpreted as an application failure, or an application failure that should have been interpreted a network failure that should be interpreted as an application success. This leads to confusing cross calls back and forth between HTTP success and HTTP failure. You also see a proliferation of objects containing partial functionality. And you will have some responder which implements some portion of the application logic that it's trying to implement, and then somewhere way across the code you'll have a further descendant of that one, which further refines it. As you noticed from the calls, we were doing a direct new on the descendant as we passed it into the as we passed it into the HTTP client call. This results in an unmanaged pointer being sent down into that system. One of the things that I saw very frequently was that the HTTP completed would rectify this, would take care of deleting this, which always is it's a pattern that tends to make me a little nervous whenever I see it. To make matters worse, some didn't. They were expecting some other form of cleanup, if they were cleaned up at all. Moving from there, the goal here is to replace that pattern with the new coroutine pattern. Coroutines, as Nat pointed out, are much more straightforward. It looks like any other C or C++ method. There's a setup. There's some sort of suspending call. You then look at the results of that suspending call, and then handle either success or failure, and then clean yourself up. All in one function, all in one place. It everything looks like just easy blocking calls, even though it's not. And in fact, you don't have to worry about it not being. Here is a very simple example of a coroutine. This simply waits for some number of seconds. You will notice that this does its wait on an LL event timeout object. LL event timeout is a derivative of the whole event pump system. Creates a timeout object locally on its own stack, writes a message, sets the timeout, and then does a wait for event on, and then writes another message and exits.
I can't resist interjecting here that the LL event timeout actually can function as a filter on some other LL event pump. And so if you're expecting a response from some event pump, but it might not arrive, you can pass it through an LL event timeout. And so you can be certain that you will either get the original event that you were waiting for or an LL timeout event. So that's the timeout mechanism I was referring to earlier when I said that, we have a safety wrapper for events that never happen.
Yes, all of the existing, as Nat said, all of the existing event pump machinery. Excuse me. All of the existing event pump machinery works seamlessly with coroutines. As Nat is so fond of saying, it just works. There is the launch of of our sample. We simply grab the singleton for LL Coros, execute a launch, give it a name. The name should be something descriptive. In this case, I tend to just use the method name. LL Coros will ensure its uniqueness. We use boost bind to reduce our function to a nullary, with 30 seconds being bound to the parameter. And again, it will simply go off and do its thing. Here's another slightly less simple example. This one introduces the this one starts to introduce the HTTP routines. The workhorse in this is the HTTP coroutine adapter. You'll notice that we create ourselves a policy. We create an adapter. The adapter handles all of the lower level event pump and suspending operations. We create the request. We may or may not want to give it options or headers. Anyway, the call of primary interest here is simply here on the. I'll go ahead and move my cursor. Here on the HTTP adapter, get and suspend. We pass it the request, we pass it the URL. At some later point, although from the perspective of our coroutine, it looks as though it happens immediately. We will get some LLSD back. We then inspect that LLSD. The LL core HTTP status has been encoded into it, and we use that status to set the results of our function and exit. Everything is just cleaned up.
Okay, so I can't resist pointing out that in this slide, all of what you see except for the HTTP coroutine adapter and the get and suspend call on that adapter is actually Monty's LL Core HTTP functionality. It may look unfamiliar to you. This is going to be the new HTTP client paradigm, but you're probably seeing this for the first time as well as the coroutine stuff. I wanted to tease apart that there's Monty's stuff, which is the bulk of this function body, and then there's the stuff that Ryder introduced, which is the HTTP coroutine adapter and its get and suspend call.
Yes. Yeah. Most of it. Yes. Most of this is just directly accessing the LL core stuff. The LL core stuff. You know, there have been a few minor additions. The PTR type is simply a shared pointer, a boost shared pointer that's been added into the function or into the class definition. Again, it's boost smart pointer, so you don't have to worry about deallocation. It just happens. Yeah, the workhorse in there is is the coroutine adapter. It interfaces between Monty's HTTP and curl libraries and the coroutine procedure, or the coroutine machinery. It keeps its own event pump for monitoring. It will handle data serialization to and from the remote services. It always uses LLSD as the parameters in, and it will always return LLSD. It also, among its other jobs, it also ensures that any default headers that are required by our application are also applied. For instance, accept the content type and the UDP port that we're listening on. All of those can be overridden from the call by adding the appropriate header, but if they're not otherwise specified, they get ejected. There are 8 primary methods on the adapter: post, put, get, delete, patch, copy, move, and cancel. Cancel is off in a land by itself. I'll talk about that in a moment. The first 7 of those represent essentially the corresponding HTTP call, HTTP method. You will also notice that sometimes there's just an undecorated version. There is a raw version. There's a file and a JSON version. The raw versions take and return an unprocessed unprocessed binary LLSD object. File will handle either a file from the an OS file from the operating system, or a file from the virtual file system, VFS. And then JSON will translate any LLSD that's passed into a JSON object, and any JSON returned from the service into LLSD for us. Not all not all of those declarations make sense in all contexts. Post being most having the most options. So you can either just post. You can post raw, post file, post JSON. Get probably get having the next. Cancel down there on the end is different. It will cancel any outstanding operation on the HTTP adapter. Yes, yeah, post most. Cancel will suspend any of the operation. Any operation which is currently suspended on the HTTP adapter will be canceled. The LLSD return will indicate that canceled state. It can be called from anywhere you happen to have the pointer to that particular HTTP coroutine adapter. Let's see. Again, I want to just emphasize the coroutine adapter. The coroutine adapter will always return LLSD. The LLSD map it returns will always be decorated with an HTTP underscore results, which is itself a map containing the status of what happened in the call. There is a static method that's provided that allows you to reconstruct the LL core status object from this, including any message that was attached from our from the returned LLSD. For any method which is tagged as raw, so get raw and suspend or post raw and suspend, the result will also have the result will also have a raw entry, which is a binary LLSD object that is simply an array of, it's simply a memory block containing the unprocessed results of the call. If the service you were talking to has returned JSON, and you've used one of the JSON methods, then any JSON return will have been converted into an LLSD object, or into an LLSD map, and also decorated with this HTTP result. HTTP headers, again provided by LL Core. So I'm not going to go into a lot of detail about them. They're simply named value pairs. You add new headers by appending. So append name value. These are optional. You do not have to create them, and you do not have to pass them in. And if you don't, then the appropriate, if they're not specified, then the default headers will be applied to the call. Again, options is also directly out of LL Core. HTTP options. Let's see, the HTTP options. Yes, it's just the LL Core stuff. Here's a much more complex example. This is the event. This does the event polling against the SIM. It uses a long poll, and we create our adapter. You'll note that this is that this particular coroutine uses a while, so it will simply continue to execute for as long as it wants to. Let's see. We set up our so we enter the loop. We set up our call. We set up our call, and we then post and suspend. Again, this is a long poll, so it will simply it pulls stuff as much as possible. Excuse me. Let's see. We get the results. We check the status, and again, this is just the LL Core HTTP status, which has been encoded into the result. If we've reached a point that we've decided, if the poll simply is returned, and we have not encountered some maximum number of problems, this would be the case in say a timeout, which will happen eventually. Then we want to wait for some period of time and retry. So we generate our retry. Here again is LL event timeout. We set it to send ourselves an event, and then there at the top we suspend. And that's, for everything this is doing. Well, I should also point out that if we do have something that comes back, we just go ahead and process it. Again, this looks like any other bit of any other bit of C++. It simply works. One of the things that we ran into was the desire to restrict the number of restrict the number of coroutines that are executing executing at a given time. Upload being asset upload being the most important of those. To do that, we created what are called coroutine pools, and these are geared towards HTTP transactions, but they certainly have a broader application. Right now, there are 3 that are defined. There's upload. There's which contains exactly one coroutine in the pool. AIS has a much larger pool of 25, and Experience Cache has 5. What happens is you simply add your co-procedure you simply request to enqueue your code procedure into one of these pools. That signal places it on a queue. That places the callable on a queue, which then triggers an LLSD event that all code procedures or coroutines in that pool are waiting on. They will all wake up in turn, check the queue. If there's something on the queue, it grabs it and starts processing. If there's not, it simply goes back to sleep and waits. Again, since these are all on a single thread, there's no need for a race. There's no race condition, and no chance of blocking against each other. Co-procedures provide a method of throttling. So one of the reasons we did this, for instance, for upload, was that I had no idea what the UI would do if I managed to if more than one upload happened to finish simultaneously, or more than one upload or more than one upload failed simultaneously. The way the original code was written, it was simply a chain of responders. So that one responder completing would create the next one and then execute it. We were talking about difficult to follow logic.
I'm going to interject here. Coyote is asking, can the coroutine lose control before all in a pool are checked? And I confess I'm not entirely sure how to interpret that, Ryder, if you have a better sense of it.
Do you mean Coyote, do you mean can a coroutine can the coroutine suspend before all the coroutines in that pool have checked the queue? Is that what you're asking?
And of course, we'll have to wait for the propagation delay.
Yes. But can the coroutines for all the if the coroutine does suspend, then it's going to behave like any other coroutine, and it won't check the queue again until it's completed. If the coroutine completes, then it gets put back into the available pool, and your Okay, I did interpret that correct. If the coroutine completes, it gets put back into the available pool. Only coroutines in the available pool will be waiting on the event the queue event. So I think that might have. I think. Let's see. When a co-procedure gets added to this pool, is everyone in the pool guaranteed to check on every pool check? Yes. Everyone that is available in the pool. So if there are five co-procedures executing in a pool of 5 elements, then there's no one available to check until one of those co-procedures finishes. Of course, I can answer any questions you have. When one of a little bit into the mechanics, the co-procedure pool. Co-procedure pool is divided into available and executing coroutines. So when a co-procedure is added to the queue, all of the available coroutines will check to see if there is something on that queue. When a co-procedure or a coroutine, when one of the coroutines in the pool finds a co-procedure on the queue, it is removed from the available pool and begins executing the co-procedure as though it were a coroutine. When it finishes, it will go back, or when it does that, it is no longer in the available pool, and so will not check. When it finishes, it will be placed back into the available pool and wait on the event. I hope that clears things up. Co-procedures are all provided with a coroutine adapter of their own. This coroutine adapter is unique to each co-procedure or unique to each coroutine, but reused between co-procedures. A co-procedure is also assigned a UUID, which can be which you can use at a later time if you've changed your mind and want to cancel that co-procedure. Say if we added some way to cancel an upload, you could say this upload's UUID is such and such. Go take it out of the queue. If that co-procedure has not begun executing, if it's still in the pool, it's simply removed from the pool. If it has begun executing, then we execute a cancel suspended or cancel suspended on the HTTP adapter that it was provided, and it's actually up to the coroutine logic to do the correct thing when it gets a canceled operation. There's the signature for co-procedures. Again, they take the adapter and they'll also be passed the UUID that they were assigned, so it knows what its ID is. Enqueuing a code procedure is fairly simple. You simply grab the code procedure manager, which is a singleton, so instant code procedure manager instance. You call the enqueue code procedure, tell it which pool, give it a name for that pool, and pass it to coproc. Again, the pool is the name of the pool. If that pool that has not been previously initialized, it will be initialized on first reference. If that pool is not known, it will be created and it will be given a default size of 5. You can adjust the pool size from the debug settings by setting the pool size plus the name of that pool size. The name is a descriptive name for the code procedure. Really, at this time, it is only used in logging. The proc is the code procedure itself. Boost bind is, in most cases, you just boost bind your code procedure into the appropriate into the appropriate form. Let's see. When you enqueue it, you're given the ID that you can then use to cancel. Here is a sample of a code procedure. This is from the experience cache. You see, we have the experience cache will do a you can either get or set the region experiences. We build up a function there with boost bind. Again, note that this we're interested in only the first parameter, which is of the default function. We get the region capability, whether or not this is a set or a get. The experiences we're interested in, and a callback, which is, we've tried to eliminate callbacks as much as possible. However, much of the UI is very fond of them. So, we still have cases where you'll have a function pointer getting or in this case, I've tried to I've set this up as a boost function, where you start seeing these things get passed around. Again, this looks like any other. This code procedure looks like any other coroutine. Comes in with the adapter. It creates its own request. It grabs the region experiences region cap. And then based on whether or not it wants to set them or get them, does a post or does a get, and suspend. It examines the results and then returns. You'll note that it erases the HTTP result from the return results, and and then calls whatever the callback that was provided to it happens to be. And that is pretty much all there is to code procedures. Are there any questions?
So stripping out the DAO reference, actually, coroutines in C++ are rather like coroutines in eventlet, and both are contrasted with, let's say, Python generators, which have a single level of suspension. In eventlet, you have the ability to create a whole chain of nested function calls and suspend from the middle of that, which is very like the C++ coroutine functionality. The underlying mechanisms are different, but yes, semantically, if you're used to eventlet in Python, it won't be strange to encounter the coroutine functionality in C++. I have a little show and tell thing, which I will just grab the screen for a second. And I want to share this. So I'm going to scroll down through here and talk about the fact that as Oz suggests, the header files for the coroutine machinery are actually somewhat documented. It's kind of funny because we have actually had this machinery in the viewer since 2009. And I am quite sure that I added some wiki documentation at that time. I will have to go back and find it, and update it. It's the recent proliferation of the coroutine pattern that occasions this presentation. With the release of the Azumeral viewer, you're going to see a lot more of this. But as I said, we've been doing this for 6 years now. And so it's not new, untried technology.
I seem to recall a media to Coyote's along with some commentary. I seem to recall seeing somewhere a MediaWiki plugin for handling for handling Doxygen into MediaWiki.
Ruslan asks.
I will put a link. I will definitely put a link to this video on the wiki.
Mm-hmm. Ruslan asks, is this based on boost context? Yes. That's the magic sauce that allows us to have a separate call stack for each coroutine. Okay, well, absent further questions on the chat itself, Ryder and I can be contacted in any of the usual ways, and we are more than willing to be asked about any questions that you have, either as they occur to you, tossing in your bed in your fevered sleep tonight, or as you encounter the code some weeks from now. please ping, and we'll be happy to help you with it. Thank you very much.